Okay, in this segment we're going to be talking about independent sources. Now these are going to be our sort of energy sources in our circuits. These will be things that supply power and also supply, let's say, input signals and things like that, test signals. So the first one is the independent voltage source. And we typically will be denoting a voltage source by a symbol that looks like this with some voltage value, let's say Vs, here off to the side. And we can think about there being a voltage across this and a current flowing through it, just like we had with our generic circuit element. And the job of an independent voltage source is to maintain Vs across its terminals, regardless of how much current it takes. Now, a mathematical voltage source could, in principle, either source or sink, either put out or take in, an infinite amount of current. So it doesn't matter how much current it takes in order to maintain a value of Vs across its two terminals. It's perfectly happy to do that. And if we were to think about practical voltage sources like maybe you've encountered before, like let's say a 1.5 volt battery, well, it's not going to be able to put out an infinite amount of current in order to maintain its voltage. At some point, it sort of just gives up. And you can imagine that a stack of, let's say, two 1.5 volt batteries makes 3. So 8 1.5 volt batteries stuck in series with each other would add up by kVL to 12 volts. And you could imagine that that stack of, let's say, I don't know, AA batteries won't be able to put out as much current as a 12 volt car battery would. And so a 12 volt car battery might be a better 12 volt voltage source or a better approximation to a 12 volt ideal voltage source over a wider range of currents than our poor AA batteries would. But here we're dealing with a sort of mathematical entity. And it's customary for us to think about these things on what's called an IV plane. So we plot the current as a function of voltage here. And for an ideal voltage source, the IV plot is going to be a vertical line at whatever Vs is. Okay, so whatever current value it takes to produce that voltage source is what the ideal voltage source will either produce or take in. And so on an IV plot like this, we have basically a vertical line for a voltage source. Okay, so that's going to be our first independent source. Our second type of independent source is an independent current source. Well, I guess I should have said with voltage sources, we're going to be using that same symbol, the circle with a plus and minus in it, both for constant voltage sources and also for time-varying voltage sources. Sometimes you'll see people use, for DC sources, you'll see something like a symbol that looks like this, which is meant to be sort of a stack of battery cells or something like that. So this is sometimes used for a constant. we're going to be using the same symbol to denote both a constant and a time-varying voltage source. So that's just an aside. So this is kind of like a battery symbol. Our second type of independent source is going to be an independent current source. In a current source, we're going to use a symbol, denote by a symbol that looks like this. We've got a circle with an arrow pointing that way, and it's going to be producing some value specified IS. And we can have, again, our voltage across it and current flowing through it, consistent with our sign convention. And what the independent current source does is it pumps out the specified current IS regardless of the value of V, the voltage, across its terminals. So its job in life is to basically pump out charge at a constant rate or at a time varying rate that's specified by whatever the voltage source, or the current source is set to produce. It could be a constant, it could be some time varying waveform like a sine wave or a step or something like that, but it maintains whatever the commanded current is, regardless of how much voltage it takes across its terminals to specify that or produce that. So again, we can do an IV plot for an independent current source, and a constant current would be a horizontal line, okay, and that horizontal line you might think would be at IS. Unfortunately, you can see that the I here, according to our sign convention, is going in the opposite direction to the way the arrow is pointing here. And so the actual IV plot, if IS were a positive number, would be down here at minus IS. Okay, so that the product of I times V is negative, right? So this is, if this is delivering power, according to our sign convention, the product of I times V with the sign convention has to be negative. And so in order for it to be supplying power, the current is going to come out of the positive terminal, which is contrary to the positive direction of our associated reference directions here, our sign convention for I and V. So it is a horizontal line, but the value of the current is actually the negative of the specified value. Okay, so that wasn't readily apparent with the voltage source, because the current that was coming out of the voltage source was basically anything, and so there was a sort of a negative sign. The current would be flowing against our sign convention for a voltage source that's delivering power to a load, but that just wasn't sort of showing up on our IV plot. Okay, so those are our independent sources. The voltage source on an IV plot produces a vertical line at the specified source value, and the current source is a horizontal line at the specified current value with the sign convention, with the sign flipped with the sign convention. Okay? So there are other types of, well, I guess I should mention that you may be more familiar or comfortable with the idea of a voltage source because you've worked with things like wall warts and batteries and things like that. Current sources, it turns out, you can also build something that approximates a current source, but it's not something you've probably sort of run into in your everyday experience. It usually takes a little bit of time for us to get to the point where we're actually building current sources in the lab. Of course, in SPICE, which is what you're going to be using as your primary experimental platform this semester, you can plop down a current source pretty easily. It takes basically a couple of op amps and a resistor to produce a current source, or it turns out that a transistor by itself is actually a reasonable approximation to a poor current source, and if you throw an op amp, a transistor, and a resistor together, you can get a very, very good current source implementation, and so we'll kind of get to that. But it turns out that you'll be thinking by the end of the course, hopefully comfortably, in terms of current sources. We're also going to talk about 4 kinds of what are called linear dependent sources. Okay, so our independent sources basically didn't depend on anything else other than the specified source value. A linear dependent source is a current or voltage source that depends on a voltage or current somewhere else in the circuit. Okay, so we have an output variable, which could either be, so output can be current or voltage, and it can depend current or voltage. And so because the output can be either current or voltage, and it can depend on either current or voltage, there are 4 different types of sources. One for each combination of current and voltage on the dependent variable and on the output variable. Okay, so we're going to talk about each of the 4 types. There is a voltage-controlled voltage source. Sometimes called a VCVS. And that's a voltage source whose source value depends on a voltage somewhere else. And that our symbol for a dependent source is generically going to be a diamond. Okay. And because it's a voltage source, it has a plus and a minus inside it, like that. And the value is going to be some A sub V times V, let's say Vx, or now let's just call it V. So A sub V is the voltage gain, and there's some, let's say, element over here in the circuit, and there's some voltage across at V. And so what happens is the circuit element over here someplace has some voltage across it, and that comes over here and is multiplied by a voltage gain, A sub V, and that produces the voltage that we would measure across the terminals of our dependent source. So this is the dependent source, and it depends on a voltage variable somewhere else in the circuit. Okay, so these dependent sources are typically used to model other types of circuit elements. Like, for instance, you could make a model for an op amp as a voltage-controlled voltage source where the voltage gain is some very large number, and the voltage that it depends on is the voltage that's measured across the non-inverting and the inverting inputs to the op amp. Okay, so we don't usually think about making a dependent source, although you can actually make dependent sources, each of the 4 types of dependent sources. practically using sort of a circuit, but usually they're used in modeling. Okay, so the parameter A sub v is the voltage gain, and that is dimensionless. Okay, so it's a number, and whatever the input voltage or the dependent variable it happens to be, it gets multiplied by that number A, and that produces the output voltage. Okay, our second type is going to be a current-controlled current source. CCCS. So in this case, there's some branch in the circuit someplace with some current flowing through it. Let's say it's I. And over here, we have our dependent current source, which again is got a symbol that's denoted by a diamond to indicate it's dependent, and it's got an arrow that indicates the direction the current is flowing. And this will have some beta times I as the source value. Okay, so beta, again, is the current gain of our current control current source. And it depends on some current flowing somewhere else in the circuit. Whatever that current is, it gets multiplied by beta, and that is how much current gets pumped out of our terminals for the output here. And so again, beta is dimensionless. It's just a pure number. And this would be, for instance, a circuit element that's used to model things like bipolar transistors, which we'll be talking about in a few weeks. The current flowing into the base terminal gets multiplied by a number that's usually on the order of about 100 to make the collector current, which is the current flowing into another terminal. Okay, so those are two of the four possibilities. The other two are a little bit more strange. Okay, we can have a voltage-controlled current source. Voltage-controlled current source, VCCS. Okay, so there's going to be some, say, circuit element here with some voltage across it, and our output is a current source, and the parameter that takes the voltage and turns it into a current is denoted by G sub m. Okay, this G sub m is called something called the transconductance gain. And that's kind of a strange word, probably not familiar to you. Transconductance stands for transfer conductance. So trans kind of has this meaning of across. So it's a parameter just like our voltage gain and our current gain that takes a voltage somewhere in the circuit and produces a current somewhere else in the circuit. But it has units. okay, because the output variable here is a current and the input variable is a voltage. That means that GM has to have units of amps per volt, so that the volts with V cancel with the volts and you get out amps. And an amp per volt is a perfectly fine way of expressing the gain value. You could say it's so many amps or microamps per volt or something like that. But it's also, this also is a unit of conductance, which is basically the reciprocal of resistance. So this has units of 1 over ohms, which is sometimes denoted by an upside down omega, which is mhos. Which is ohms spelled backwards. Now the symbol G is the one that we customarily use for conductance. So G denotes conductance by convention. So you may be wondering what the subscript of M means. The M stands for mutual. It used to be that this was also called mutual conductance, and sometimes it still is called mutual conductance, but it's much more common in today's parlance to call it transconductance, and so that's the way we'll be calling it. But it also is sometimes called mutual conductance, and the symbol is still GM. So it's a little bit of terminology to get used to. So that's the first of our strange ones. Okay, voltage-controlled current source, and the other possibility is the current-controlled voltage source. So we can have current-controlled voltage source. Or CCVS. And this, as you might be able to guess, there'll be some current flowing in some wire someplace in the circuit, and there'll be some voltage source, and there'll be some R sub n times I to produce the output voltage. Here Rm is the trans resistance, gain, also called mutual resistance. And Rm has units of so many volts per amp, which is just ohms. Okay, so we have to cancel the amps that we have in the dependent variable and produce a voltage at the output. And so Rm will have units of resistance. And believe it or not, you've actually all probably built a current-controlled voltage source or an approximation to such a device. Back in ISIM, you probably recall building a circuit that looks something like this, where you have, maybe this was at some reference voltage Vref, and you put an op amp with some resistor, and maybe you had a photodiode or something here. Actually, this is probably ground. and there was some light shining into the photodiode, maybe through your finger, and there was some resistor here, and the op amp held this input node V minus at about 0 volts. The current flowing through the diode flowed through the resistor, and V out, if this was I in, V out was just I in times R. And so the current flowing in this diode here led to an output voltage over here through some resistance R. And so this is sometimes called a trans resistance amplifier. And this is basically a current controlled voltage source implementation. So this is something you've met before, but it's also sometimes used to model other kinds of circuit elements. Okay, so these are called linear dependent sources because there's just a proportionality between the dependent variable and the output of the source. You could imagine more complicated scenarios where maybe there's some function, some functional form that takes the dependent source and turns it into a voltage. And it turns out that in LT-Spice, our dependent sources are more flexible than just these linear dependent sources, where you can actually specify sort of an arbitrary function of actually more than one variable. But you can also use that to implement a simple linear dependent source. Okay, so we may not be using these 4 types of sources very much explicitly in our modeling, but it's important for you to understand what they are, and it's important for you to understand what the symbols mean. These concepts of transfer conductance and transfer resistance, or trans resistance and transconductance, are going to be important for us as we go through the term. Okay, so that's it for this segment, and we'll see you in the next one.